So today, what we're going to do is we're going to pick back up where we left off. We were dividing polynomials. Remember, we're taking two polynomial expressions and dividing them and getting another polynomial with some remainder. We did that with long division, but then we used synthetic division. And the last thing we saw was that when we did synthetic division, we had x to the fifth minus x to the third plus 2x squared minus 4x plus 9. And we divided it by x minus 2. And we got a polynomial plus remainder 33. Remember that? When we took x to the third minus 9x squared plus 9x plus 10, and we divided by x minus 2, we got a polynomial with remainder 0. And we saw that when we plugged in 2 into each of those functions, it happened to give us the remainder. So f of 2 was equal to the remainder of 33. At g of 2 was equal to remainder 0. Okay, when I say the remainder, I mean the remainder after division, obviously. Let's do one other example. Let's take x to the fourth minus 3x to the third plus 9x minus 10 and divide it by x plus 5. So just as a reminder, we put negative 5 out as the number. Again, some people like to put a box around that, some people don't. And then I start dealing with the coefficients of x to the fourth. That's 1. Coefficient of x to the third is a negative 3. Notice that there's no x squared, so we got to put a placeholder of 0. Don't forget about that. Anytime we don't have a term, put a placeholder there. And then 9, and then negative 10. 1 drops down. Negative 5 times 1 is negative 5. These add up to give me negative 8. Negative 5 times negative 8 is a positive 40. Add those two up and you get 40. 40 times negative 5 is equal to negative 200. When I add 9, I get negative 191. If I take negative 191 times negative 5, I get 955. Add those two up, I get 945. So that means when I divide these two polynomials, I end up, remember we started with an x to the fourth term, so down here we're starting with an x to the third term. We end up with 1x to the third minus 8x squared plus 40x minus 191 with remainder of 945. Is that pretty straightforward? And it turns out one kind of nice way to check your answers is what I was just talking about. Think of having a function as x to the fourth minus 3x to the third plus 9x minus 10, and go ahead and calculate f of, in this case, -5. When I plug in a -5, I get -5 to the fourth. Make sure you put that negative in parentheses. Minus 3 times -5 cubed plus 9 times -5 minus 10. And sure enough, I get a 945. That's a good check that you've done the division right. If you do synthetic division and your remainder comes out as 945, but you plug in -5 and you end up getting 13, you know something's off. One of those two has to be off. Now, by the way, these last couple of examples, the ones where we had remainder of 0 and the ones where we haven't had remainder of 0, mean something. If I have f of x divided by x give me a quotient, so dividend over divisor gives me quotient, with a remainder of 0, what that implies is that f of x can be rewritten as quotient times divisor. Get that? So if we have remainder 0 when we divide, then f of x can be written as a product of two polynomials, where our divisor is one of the factors. So we call our divisor g of x a factor of f of x. And what's the nice thing about having a remainder of 0? Well, it means that when I plug it in, I get out a 0, right? When I plug that number in, I get out a 0. So, in other words, zeros of polynomial functions are going to correspond to the factors of those polynomial functions. Does that make sense? If I go back to this example where I had g of x equals x to the third minus 9x squared plus 9x plus 10. So I have this example, g of x. We knew that when we took g of x and divided it by x minus 2, is that right? That came out And now I forgot what that was. Let me go ahead and do that synthetic division for that, because I forgot. No big deal. All right, so we got x squared minus 7x minus 5 when I did that. So because I got remainder 0, I could say this g of x can be written as x minus 2 times x squared minus 7x minus 5. And also, because I've written it that way, or you can see it in a different way, when you plug in 2, we know we get out of 0 because we have the remainder of 0, or you can see it right here. Does that make sense? So x equals 2 is a 0 of g of x. So the zeros of the functions are going to correspond with factors that look like x minus those numbers. Right, get that? So the zeros of the function correspond to factors of x minus whatever that value is. And this is the key to finding zeros of polynomial functions. And we're going to do a lot of work where we find zeros of polynomial functions in the next section. In fact, that's what the entirety of the next section is just finding zeros of polynomials. Okay. So we already know that a zero of a polynomial function is a number that I plug in and I get out 0. We've talked about that. We've talked about the fact that these are corresponding to the x-intercepts when the 0 is a real number. If you ever hear the phrase root of a polynomial function, that means the same thing too. All right, so a 0, a root are the same things. X-intercepts correspond to zeros that are real numbers. Okay, that's what I have right here. So if our 0 happens to be a real number, then we know we get an x-intercept. All right. So if you were given a graph of a polynomial function and you were asked to find the real zeros, all we have to do is look for the x-intercepts. So like on this example, the real zeros are when x is negative 3, when x is positive 1, and when x is positive 2. That's where this graph crosses the x-axis. So those are going to be the real zeros. Now there might be some complex zeros that we don't see here. Can't see complex zeros on a graph. But the real zeros are when x is negative 3, when x is 1, when x is 2. So if we're looking for zeros, if we're looking for real zeros, I can use the graph. As long as I can kind of see where it hits the x-axis. But we want to find all the zeros, even if they're ugly, even if our graph hits the x-axis in weird spots, right? It might be difficult to see a zero if the zero is like the square root of 14. You say, well, square root of 14, that's above 3, but under 4. You know, it's hard to see where it crosses if it's that. So we're going to develop some tools for finding zeros. One of the tools is knowing that every polynomial of degree n can be factored into a product of n linear factors over the complex numbers. So if we're using complex numbers, if I have a polynomial function, I can always factor that into a product of x minus a number times x minus another number times x minus another number n times. Where these numbers are complex numbers. They might also involve some ugly square roots as well. So we can always factor it this way. Now, one other thing, I'm writing them as r sub n minus 1, and so on and so forth. You might have repeated factors. You might have r minus 2 times another, excuse me. You may have one of your r be a minus 2 and another r be a minus 2. That makes sense. So you might have like x plus 2 as one factor, and then x plus 2 is another factor somewhere else. But every polynomial of degree n can be factored into n linear pieces as long as we're allowing complex numbers. If there are repeated factors, then we say those linear factors have multiplicity of whatever it is. If I have 3 factors of x plus 2, then I say the factor x plus 2 has multiplicity of 3. There's 3 of them. And just like we were describing earlier, if we have a linear factor, that means I have a zero of my polynomial function. Okay. So we'll also say that the zero of whatever r is has multiplicity of whatever the number is. So if x plus 2 occurs 3 times as a factor, then we say negative 2 is a zero with multiplicity of 3. So let's take an example of 2 different functions that have already been factored. We have f of x, which is equal to 2 times x minus 3 squared times x minus 6 to the 4th power plus x, or not plus, times x plus 2 times x minus 11. And then I have a g of x, which you can see on the screen. I'm going to write that down. We have x plus 4 times x minus 1 raised to the 5th power times x plus 2 minus 4i times x plus 2 plus 4i times x minus 7 raised to the 3rd power. I got it written down right. So if we want to find the zeros, with their multiplicity, all we have to do is look at what would make this into a 0. We'd say, what do I need to plug in x to make this 0? This is x minus r, so the r is going to be what you need to plug in to make it 0. So this factor corresponds to a 0 of 3, which has multiplicity of 2 because that factor occurred twice. This factor corresponds to a 0 of 6 with multiplicity of 4 because that factor occurred 4 times. Did I get that? This factor of x plus 2 corresponds to a 0 of negative 2. And it has multiplicity of 1, because it just occurs once. And then lastly, x minus 11 corresponds to a 0 of positive 11, and that has multiplicity of 1. So we have a 0 of 3, a 0 of 6, a 0 of negative 2, and a 0 of 11. Those are the numbers that you can plug into your function and get out a 0. And there's 2 factors that correspond to the 0 of 3, 4 factors that correspond to the 0 of 6, 1 factor that corresponds to 0 of negative 2, and 1 factor that corresponds to the 0 of 11. By the way, this also means that there's going to be 4 x-intercepts as well. 4 places where our function touches the x-axis. One at x equals 3, another at x equals 6, another at x equals negative 2, another at x equals 11. Because those are all real zeros. If that makes sense. Go ahead and list out the zeros with the multiplicities of that one, of the g of x, and then afterwards in your head think, how many x-intercepts does this mean g of x will have to have? All right, these list out pretty quickly as long as we know what we're doing. The zeros are going to be -4, 1. Be careful when you have complex numbers, because it's always x minus r. So this whole thing is being subtracted. This one technically is -2 plus 4i. Can you follow that? This one is the -2 minus 4i. Did you get that? So it's like, what do you plug in? You get 0. One of them is -2 plus 4i. That's the first one here. And then the second one is a -2 minus 4i. I always ask, what value of x produces 0 in the parentheses? Okay. What value of x produces 0 in the parentheses? If you plug in a -4 for x, it produces 0 there. If you plug in a 1 for x, it produces 0. Here, you'd have to plug in -2 and then a plus 4i so that those terms cancel. Here, you'd have to plug in a -2 minus 4i so that those terms cancel. Here, you'd have to plug in a 7 so that that cancels. And multiplicity of -4 is a 1. Multiplicity of 1 is a 5. For both our complex zeros, we get a multiplicity of 1. And then with 7, we get a multiplicity of 3. Just because that's how many factors occur. By the way, how many x-intercepts would we have here right now? 3, exactly, 3. We have 3 real zeros, so we're going to end up with 3 x-intercepts. Okay, the complex zeros don't give me any x-intercepts, so we end up with 3 x-intercepts since we have 3 real zeros. Now we're going to state something formally that we've actually seen earlier in a couple of examples. Okay. When we were factoring quadratics and getting the zeros for quadratics, solving quadratic equations, getting the zeros of quadratic functions, we saw that if our polynomial had real number coefficients, then the complex number zeros have to occur in conjugate pairs. Guys remember doing that? Solving, you use the quadratic equation. If you use the quadratic equation and it spits out complex numbers, non-real complex numbers, then those occurred in conjugate pairs, like a 3 plus 2i and a 3 minus 2i. That helps me know that if I found 1 0, that's some complex number, and my polynomial has real coefficients, then I know I'll have another 0, which is a complex number, and it'll be the conjugate pair. So that's one tool that we can use. So we have our first tool that says we can factor things over the complex numbers into linear pieces. Now we know that if we have a complex 0, then we'll have another one, which is its conjugate pair. Okay. Now, if you think about those two things put together, When you take x minus a complex number, and then multiply by x minus its conjugate, what you get is a quadratic with real coefficients. That makes sense? So you'll get x squared back to get that. You get x squared minus 2ax plus a squared plus b squared. So you get real coefficients in your quadratic when you multiply conjugate pairs together. Things drop out, I'm ignoring those. But that means that if we want to factor over the real numbers, then we can factor it into linear pieces where the roots are real. And then anytime I have a complex root or a complex zero, I'll have its conjugate pair. When I take those two factors and multiply them together, it'll be a quadratic. So every polynomial with real coefficients can be factored into linear and quadratic pieces with real number coefficients. Now, here's the nice thing. We know how to solve these. If we set the linear piece equal to 0, we know how to force that to be 0. We also know how to solve quadratics. So when I set the quadratic equal to 0, I can use any of my quadratic tools. So standard solving of linear equations and solving quadratics are the tools that we're going to use over and over and over again to find zeros of polynomial functions. Okay. That along with doing some division. Now, another little property, if you think about it, if it's a polynomial with real coefficients and it has odd degree, so the leading term is like x to the third or x to the fifth or x to the seventh, then it has to have one real zero. You can see that in two ways. Using the previous theorem of factoring all of these quadratics just multiplied together can only give me even power polynomials. So if I have an odd power polynomial, I need at least one linear piece. Okay. So I can think of it that way. Or I can just think of the end behavior. Remember, if we had a polynomial function whose degree was 3 or 5 or 7, then the end behavior was such that one side shoots off to positive infinity and the other side shoots off to negative infinity. So intermediate value theorem would say we're going to have to cross the x-axis somewhere, right? So this brings us to actually doing the problems. to actually finding the zeros of a polynomial function like p of x equals x to the third minus 5x squared minus 18x plus 72. Now, we're going to be given originally that x minus 3 is a factor. We'll show how to get that without being given it in a little bit. But for right now, we know that x minus 3 is a factor. If I know x minus 3 is a factor, then I know that when you divide this polynomial by x minus 3, you should get a polynomial. So we're going to use division to figure that out. And since x minus 3 is a linear piece, looks like x minus r, I can divide using synthetic division. So I take 3, 1, negative 5, negative 18, 72. 1 drops down, 3 times 1 is 3. I get a negative 2. Negative 3 times negative 2 is a negative 6. That is negative 24. Negative 24 times 3 is a negative 72. And sure enough, I get a remainder of 0. So that's good. So this means when we divide, we get x squared minus 2x minus 24. That means my original polynomial, instead of writing this as this cubic, all multiplied out, I can instead write it as x minus 3 times x squared minus 2x minus 24. We get why that is? Just multiply both sides of this equation by the quantity x minus 3, you get that. Now our goal is to find the zeros of this polynomial. I know that 3 is going to give me a 0. Now all I have to do is break this up. If I can factor this, I'll factor this. If I can't factor this quadratic, then I'll use my quadratic formula. All right. Let's look and see if we can factor. Factors of negative 24. We would get things like 2 and negative 12, 3 and negative 8, 4 and negative 6. And sure enough, the ones that add to negative 2 are 4 and negative 6. Okay, follow this? And so that means this quadratic can be factored into x plus 4 times x minus 6. That quadratic is not always going to be able to be factored. So So if I'm looking for zeros, I'm basically asking to solve this equation here, right? I'm asking to solve this equation. So we're going to get zeros of x equals 3, x equals -4, and x equals a positive 6. Each of those have multiplicity 1, but everybody okay with that? So the goal for finding zeros is to essentially find an initial zero and then break down our polynomial into a factor of smaller degree polynomials. And then I keep doing that until I get down to the end, and then I just say, well, now let's just solve this equation, in this case, these 3 equations. Okay. Sometimes our quadratic won't factor, and then we'll have to use the quadratic formula. We'll say, well, set this quadratic equal to 0, and use the quadratic formula to find the other 2. I want you to try this one on your own. We have a function which is x to the 3rd minus x squared minus 37x minus 35. And we know one of the zeros is x equals -5. Maybe you saw that on the graph. Maybe we came up with it by plugging in some different numbers. But we know x is -5 is a 0. I want you to find all zeros for that function. Try this on your own. so when it says x equals -5 is a 0, that's like saying x plus 5 is a factor. Those two things are interchangeable, right? So x plus 5 is a factor and x equals -5 is 0, interchangeable. Same on the last example. We were given a factor, we could have immediately said, yep, I know there's a 0 at that spot. So those are interchangeable. So that means I can divide my polynomial by x plus 5 and I should get a remainder of 0. -5 times -6 gives me a positive 30. Add that, I get -7. -5 times -7 is a positive 35. Add those, I get, sure enough, remainder 0. So that means my function, well, let me rewrite this. So when we divide, I get x squared minus 6x minus 7 with no remainder. Which means my function output can be rewritten as x plus 5 times x squared minus 6x minus 7. Now I'm looking for zeros, so I'm trying to solve output equaling 0. X plus 5 is as simple as we can make it. We try to factor that quadratic if we can. In this case, there are factors of -7 that add to -6, in particular 1 and -7. So I can rewrite that quadratic and factor it as x plus 1 times x minus 7. All right, that. And so I get zeros in 3 spots when x is -5, when x is -1, and when x is a positive 7. And since I have 3 real zeros, I know this original function is going to cross the x-axis 3 different times. Okay. We're going to have 3 x-intercepts. 1 at -5, 1 at -1, 1 at 7. Let me do another one. We have g of x equaling x to the 3rd minus 4x squared plus 9x minus 10. And I know that x minus 2 is a factor. So we're trying to find zeros, and we know that x minus 2 is a factor. By the way, that's the same thing as saying x equals 2. X is equal to 2 is a 0, right? So I'm going to do the standard thing. In this case, synthetic division. By the way, you can also use long division, but it just takes longer, so I never do that. Synthetic division is a lot nicer when we're dividing by x minus a number. So 2 times 1 is 2. Negative 4 plus 2 is a negative 2. 2 times negative 2 is a negative 4. 9 plus negative 4 is a positive 5. 2 times 5 is a positive 10. Negative 10 plus 10 is 0. So when I divide by x minus 2, I end up with x squared minus 2x plus 5. So I know that my function can be rewritten as x minus 2 times the quadratic x squared minus 2x plus 5. Now my first step is going to be, can I factor that quadratic? Trying to solve the equation z equal to 0. There are no factors of 5 that add up to negative 2, right? So that is not factorable over the integers. So I can't factor it. If I can't factor it, then basically my other option is just to set x minus 2 equal to 0. I already know that. And then set this quadratic equal to 0 and solve this quadratic equation through some other technique other than factor. We know it's not going to factor, so we just set this up. And what I would probably do is use quadratic formula, opposite of b, plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. The inside of the square root is a negative 16. That's 4 minus 20. So we're going to end up with complex number answers. I'm going to actually just do it this way. So this original linear piece set equal to 0, don't forget about that. That still comes down. I get 1, 0 as x equals 2. And then my other zeros, one of them is going to be 1 plus 2i. And the other is going to be the complex conjugate of that, 1 minus 2i. So those are my 3 zeros for this polynomial function. Okay with that? I get 3 zeros, one of them is real, and therefore if I graphed that polynomial function, I'd have 1 x-intercept. And again, notice my complex number, non-real complex number solutions occurred in conjugate pairs. So when this thing doesn't factor, you just use the quadratic formula. Doesn't factor over the integers. Now there are situations in which this won't factor over the integers, but you'll still get real numbers. They just won't be nice integer values. Does that make sense? So you could get like 5 plus the square root of 8, or square root of 19, or 5 minus the square root of 19, something like that. And that's fine as well. So you might get real number answers, or you could get, like in this case, complex number answers by completing the square. By, excuse me, quadratic formula. Is that all right? Not too crazy? Try this one on your own. All right, so let me go through this. When we're looking at coefficients, or excuse me, let me rephrase this. Let's start here. We know that x equals -1 is a 0, which tells me x plus 1 is a factor. Okay? So I can divide by x plus 1, and I should get a nice polynomial with no remainder. So we test that through synthetic division. 1 is the coefficient of x to the third. The next coefficient has to be a 0. That's the coefficient of the x squared. Don't forget that one. There's no x squared term, so put a 0 as a placeholder. And then 12, and then 13. Those are my coefficients. Drop 1 down, multiply times -1. Add those two, multiply times -1. Drop, or add those two, multiply times -1, and sure enough, I got a remainder of 0. If I didn't, something went wrong. Either the question was wrong or the math was wrong. Either it actually wasn't a factor or I did the math wrong. So this means that when you divide, you get x squared minus 1x plus 13. There's going to be no factors. There's going to be no integer factors of x squared minus x plus 13. You try to factor 13, there's no 2 that add up to -1, right? And so we're going to set this thing equal to 0. And then each one of these factors, the linear piece and the quadratic piece, are going to be set equal to 0. The linear piece gives me x equals -1. Obvious. And then for the quadratic piece, we're going to use the quadratic formula. So opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. We get a square root of a -51 in parentheses, and then divided by 2. Well, 1 plus or minus square root of -51 divided by 2. 51 is not a perfect square. In fact, it doesn't even have any factors that are perfect squares, so I can't simplify that at all. Except for square root of the negative is the I, right? So I'll pull an I out, pull the negative out, put it as an I. That's it. So we get 3 solutions. One of them is x is equal to -1. The other is x equals 1 plus I times root 51 divided by 2. The other is 1 minus I times the square root of 51 divided by 2. You could have written those complex solutions in different ways if you'd like. If you had wanted to write those as real parts and imaginary parts, you could just split up by dividing each piece by 2. Right? That's 1/2 plus root 51 over 2 times I. You divide each piece by 2. And this is 1/2 minus square root of 51 over 2 times I. And if you wanted a decimal approximation, then you can just use the decimal approximation, whatever that happens to be. Any questions about that one? Straightforward. So we're trying to find zeros, and what we do is we start with one thing that we already know, and then we break down a higher degree polynomial into a product of lower degree polynomials. And these lower degree polynomials are ones we can set equal to 0 and solve. Now there's going to be 2 different things that we do here. 2 different, I don't know, curveballs, if you thought like that. One we'll do later is saying, what if we know that we have a 0, but our 0 is a complex number instead of a real number, or instead of an integer? So what would we do in that situation? The other situation is the one we're going to focus on right now. What if we don't know this? What if we don't know any information, but we're just given a cubic polynomial and asked to find the zeros? What if I'm not already given that one of the zeros is -1? Well, there's a tool that we can use called the Rational Zeros Theorem. Now, this isn't a crazy thing. Think of our polynomial as having all integer coefficients or rational number coefficients. Okay? In the ones I give you, it'll be all integer coefficients. So imagine our polynomial has all integer coefficients, just like all the ones we've been dealing with. What the Rational Zeros Theorem says is that any rational zeros are going to have the form b over c, where b is a factor of my constant, and c is a factor of the coefficient of the leading term. That makes sense? Most of the time in this class, I will give you a lead term, which is just 1, most of the time. So the only really factors we're looking at are really 1 or -1. But this would work for any polynomial. So if we have a polynomial whose coefficients are rational numbers, then any rational zeros are going to have the form b over c, where b is a factor of the constant and c is a factor of the lead coefficient. So this gives me a place to look for zeros. I'll talk about why this has to happen in just a moment. But let's say we're given this function, f of x is equal to x to the third minus x to the second minus 10x minus 8. And we want to find the zeros of that polynomial function. I know we're using b and c in a different way than we use them with quadratic functions. Hopefully that's not throwing you off. This is just how the rational zeros theorem is written. I guess we could use different letters, but that can get confusing as well. So our rational zeros are always going to look like a fraction b over c, where b is a factor of, b is some factor of the constant. So I'm going to look at all the factors of -8. And I'm going to list them all out. So we could do 8. We could have done -8. We could have done 4. We could have done -4. We could have done 2. We could have done -2. We could have done 1. We could have done -1. So those are all of the integer factors of -8. C is the factors of my coefficient of 1. The only two options there are 1 and -1 for integer factors. So my options for zeros, for rational zeros, excuse me. In other words, the b over c, I could take 8 over 1, -8 over 1, 4 over 1, -4 over 1, 2 over 1, -2 over 1, 1 over 1, or -1 over 1. Those are all just the actual b values. And then what's going to happen when I take those numbers over a -1 is I'm just going to get their opposites, which are already in the list. Okay with that? Like if I took an 8 over -1, that's -8, which is already in the list. -8 over -1, that's +8, that's already in the list. So I only need negatives on one or the other. I could actually just use the +1 for the C because I've already listed out the negatives. So those are my only options for rational zeros for this problem. And so we just check them. We know that since this is degree 3, it has to cross the x-axis somewhere, right? So at least one of these is going to hit. So at least one of those is going to hit. Maybe 3 of them will hit because it's degree 3. Maybe only 2 of them will hit, but at least 1 and maybe 3, maybe up to 3. So we check them, and we're just going to plug in these numbers. Plug in 8, plug in -8. plug in 4, plug in -4, plug in 2, plug in -2, plug in 1, plug in -1. And in each case, we'll just calculate what happens. Let's start by plugging in the 8. 8 raised to the 3rd power minus 8 raised to the 2nd power minus 10 times 8 minus 8 gives me 360. Are we okay with that? Look at an 8. By the way, that means 8 is not a 0, right? When the x value is 8, we're very far away from the x-axis. 8 is not a 0. Let's check 4. I'll just go straight across and then across here. Okay. So you can do it. You can do this in whatever pattern you want. But 4 raised to the 3rd power minus 4 squared minus 10 times 4 minus 8. I have that in my calculator. That does give me a 0. So 4 is a 0 of this function. Now, if you wanted to, you could stop right here. You could say, I know 4 is a 0 of the function, and therefore, x minus 4 is a factor, and then I could go through the exact same process I did in all those previous problems. Okay? Does that make sense? In all the previous ones, I could just stop right there and find the quadratic and so on and so forth. But oftentimes, it's worth my time to check these other numbers because we might get other zeros. We might get other rational zeros. And that would save me time over having to do the division and go through that process. That everybody understand that? So let's try the other ones. 2 to the 3rd minus 2 squared minus 10 times 2 minus 8 gives me a negative 24. That's not going to work. Try 1. When I plug in 1, I get a negative 18. Let's try a negative 8. Yeah, sorry. When I try a negative 8, I get a negative 504. Not looking good, is it? Try a negative 4. A negative 48. Trying a negative 2. That gave me a 0. Trying a negative 1. That also gave me a 0. So now I know that there are 3 factors, 3 real numbers that when I plug them in, I get a 0. I can just write the solutions right here. I know it's degree 3, so it can factor into most 3 linear factors. If I wanted to, I know exactly what those factors are going to be. They're going to be x minus 4, x plus 2, and x plus 1. So I have my linear factors. I know what they are. I could skip that. I don't technically have to write that. If I don't want to. Because I already know what the zeros are. There's 3 zeros. That's it. Why can't I have more than 3 zeros? Well, I can't have more than 3 zeros because this is degree 3. So you get at most 3 zeros. And with multiplicity, we know that the zeros with multiplicity are going to add up to 3. Is that right? So rational zeros theorem can do that. Notice that by just plugging in a few extra numbers, it actually saved me some time. I didn't have to do the division and that whole process because we got actually 3 integer numbers that gave me 0. But if just one of these turned out to be 0 and none of the others did, then we could do the division and then quadratic formula on the quadratic remaining part. Just like we did in the previous example. So that being said, I want you to try this example on your own. Now, I forgot to say something last time. This is just an observation. I was going to say why the rational zeros theorem works. If you remember, the polynomial from last time had a constant of -8 at the end. The reason why the rational zeros theorem works is because when you factor these things, -4, 2, 1, had to multiply to give you that constant at the end, right? Of -8. So that's why the rational zeros theorem works. And whenever we factor this new polynomial in, these three numbers are going to multiply to give me 6. Now, that's because this coefficient is a 1. Obviously, if that coefficient were something else, then I'd have to maybe divide by that coefficient in the process. So, all right. So anyways, we have a 6 here. Factors of 6. I could do 6 times 1. I could do 3 times 2. So 6, -6. 3, -3, 2, -2, 1, -1. Options for my coefficient are just 1 and -1 again. In this class, I'm not going to give you a million different options. Like you can imagine, if my constant was like 720, there's lots and lots and lots of factors to check. Okay. If my coefficient were also 24, there'd be lots and lots and lots of factors to check. Okay, so think about all the different factors of 720 divided by all the different factors of 24. That would give me lots and lots of options. With the ones I'm going to give you, we're not going to have a crazy number of options. Like in both this case and the last case, we have 8 options to check. -6, -6, 3, -3, 2, -2, 1, and -1 are all of my options I can check. And then I start plugging those in. I'm going to do it this way. Hopefully I'll save some space because I know I'm going to need it here in a second. What I like to do when I plug in a bunch of numbers into the same function, well, there's a couple of different ways you can do it. One, you could graph it and just do the trace. You guys know how to do that? So you could do that. You could graph it and then trace. As long as your window has x values between 6 and -6, you're good to go there. You can also do the second enter. Once you plug in like a -6, you hit a second enter and then go back and change the 6 to a 3. Now you've plugged in -3. Okay. So you can do this efficiently using your calculator by either using the trace menu on the graph or by doing second enter, and then just changing the number you plug in. You guys know what I'm talking about there? Or do you want to see it? Let me go through that. I'll go through both options. I've actually already done the second enter option. So you'll see that on my calculator. So I've already done this, but let's say I deleted plugging in 2, and I wanted to plug in 2 now. Well, I've already plugged in 1, so I just hit second enter, and now I have the exact same function where I plugged in 1, and I just go replace every 1 with the number 2. And then enter, and then that's a lot faster than typing everything in all the time, right? So that second enter option works well. The other thing I could have done is go to the graph, x to the third plus 2x squared minus 17x plus 6. I'll make sure that we're doing a standard window because that has x values between -10 and +10. And then if I trace, I can just plug in 6. That'll plug in 6 into the x value, and that gives me an output of 192. I can plug in 3 into the x value just by hitting 3, and that gives me a 0. I can plug in 2 into the x value, that gives me a -12. I can plug in 1, that gives me a -8. I can plug in a -6, that gives me a -36. Plug in -3, that gives me a 48. Plug in a -2, that gives me 40. And then plug in a -1, gives me a 24. So of these 8 options, only x of 3 gave me a 0. So that means I have 1 rational zero. Obviously, as we can see, this graph crosses the x-axis at 3 points. That means the other 2 are irrational, right? My other 2 options are irrational values, okay? Which come in irrational conjugate pairs. So, if I want to find an approximate, I could probably find the approximate with my calculator. If I wanted to find the exact value, then I'd say, well, now I know x equals 3 is a 0. So I take the x to the third plus 2x squared minus 17x plus 6, divide it by x minus 3. This should look very familiar. This is what we're doing the first few of these, right? So we get 3 synthetic division. Three times 1 is 3. 5, 15, -2, -6, -0. And so we have P of x being equal to x minus 3 times the quadratic x squared plus 5x minus 2. We actually know x squared plus 5x minus 2 is not going to factor, because if it did, I would have saw those zeros over here already. So we set each piece equal to 0. Just like we did in the first few examples there. This is x equals 3, obviously. This opposite of b plus or minus square root b squared minus 4 times a times c all over 2a. It's going to be 25 plus 8, so that's a 33. And there you go. That's it. So now we can see the 3 zeros, and this gives us the exact value for the other two. One of the zeros is going to be -5 plus the square root of 33 over 2. That's all over 2. The other is going to be -5 minus the square root of 33, all divided by 2. And if Moodle asks for the exact answers, then you can give them like this. If it asks for the approximate answers, round it to a couple decimal places, then just stick this in your calculator and round it a couple decimal places. Okay. Both of these are real but irrational. And that's why we saw that graph crossing at 2 different points and not pick up with our rational zeros, because those were irrational zeros. Make sense? So, anyways, that's as difficult as the Rational Zeros Theorem gets. Okay. By the way, everything I've done so far has been x to the third starting out. If we have a higher degree, like x to the fourth, all these tools still work out. Okay. So let me do this example because it's actually quite nice. X to the fourth, so my polynomial function has output of x to the fourth minus 2x to the third minus 8x squared minus 6x minus 1. If I'm looking for the rational zeros theorem, I look at my constant, which is a -1. There's only 2 factors, 2 integer factors of that, -1 and +1. Only 2 options. And then my coefficient, also -1 and +1. Coefficient x to the fourth. So the only options for rational zeros are +1 and -1. So this is going to be really easy to check. In fact, other than plugging in 0 into a polynomial, 1 and -1 are really nice to plug into polynomial. You guys know why that is? If I plug in 1, any number to the fourth power, any number to the third power, it's 1 to the fourth, 1 to the third, 1 squared, 1 to the first is just 1. So basically, when I plug in 1, I just have the coefficients. I have to check. So easy to do if you want to. So let's plug in 1. This is going to turn into 1 minus 2 minus 8 minus 6 minus 1. Not going to give me 0. So what we're getting is negative 16. Wait. What happens when I plug in -1? Well, every even power turns into a +1. Every odd power turns into a -1. So it just flips the sign. So we end up getting 1. This would be a +2. This would be a -8. This would be a +6. And this would be obviously a -1. That does give me 0. So now I know that -1 is a 0, which means that x plus 1 is a factor. In fact, if you're really clever about this, you'd say, wait a second. All these irrational numbers have to occur in conjugate pairs, irrational conjugate pairs. All of the complex numbers also have to occur in irrational conjugate pairs. So I should have expected, since this is degree 4, I should have expected 2 rational zeros. Right? Either 2 or 0 or 4 rational zeros. Okay. I have 1. That probably means that has multiplicity of 2. That makes sense? So we'll check that out when we get to it. So that's just a little what's going on in my head, right? It's degree 4. Conjugate pairs can only take out 2s at times. So we either should be at 0, 2, or 4 rational zeros. Okay. So I'm guessing that has multiplicity 2 right now. Yes. But we'll check it out. So x to the 4th minus 2x to the 3rd minus 8x squared minus 6x minus 1. Divide that by x plus 1. There we go. So we get x to the 3rd minus 3x squared minus 5x minus 1. And then this is a rational polynomial function. So you could plug in 1, see what happens. Plug in -1, see what happens into this. And sure enough, if you plug in -1 into this, you'll also get a 0. So I'm going to take that thing and divide x plus 1. Divide that by x plus 1 as well. You okay with that? -1. One shoots down. 1 times -1, -1. You get -4 times -1 is a positive 5. -1 times -1 is a positive 1. Give you 0. Exactly what we thought, right? That was our intuition, hopefully. I don't expect you to be able to do that intuition stuff, but that's kind of how that goes. So that means when I divide that by x plus 1, I get x squared minus 4x minus 1. So let's think about what my function started out as. this fourth degree polynomial. After I did my first division, I knew it was going to look like x plus 1 times this third degree polynomial. This third degree polynomial can be further broken into another copy of x plus 1 times this quadratic. Okay, get that? So that's what we're getting. That quadratic is not separable over the integers. So we're going to be left to use quadratic formula on that quadratic. So I look for rational zeros, do a couple of division problems. And now I have this. By the way, I don't need to set x plus 1 equal to 0 and then another x plus 1 equal to 0. We know that that's going to produce it's going to produce a single 0 of x equals -1 with multiplicity of 2. But I will set this equal to 0 and then quadratic formula. That becomes 4 plus or minus the square root. So it's going to be 16 plus 4, which is a 20, divided by 2. You can simplify root 20 if you'd like. 20 is 4 times 5. 4 is a perfect square. So you can, if you like, simplify this to 4 plus or minus. Square root of 4 is 2. Square root of 5 does not simplify. So we get 3 zeros. One of them is -1. The other, again, simplifying by dividing everything by 2. I get 2 plus 1 times root 5. And then the third would be a 2 minus the square root of 5. Okay with that? It's just a division. And then I set my pieces equal. Hopefully the whole goal here is to break down this larger degree polynomial into linear pieces and quadratics, and then solve the linear pieces very easily, solve the quadratics either by factoring or by quadratic formula. Right? So we break down large polynomials into linear pieces times quadratics. Solve the quadratic pieces, solve the linear pieces. All right. Now, let me show you how to do this type of problem. We actually don't need to use the Rational Zeros Theorem, although it says that in the directions. Let's find the zeros for this polynomial function. So now we know how to do the rational zeros theorem. We've done that a number of times. If we wanted to try a rational zeros theorem on this, that'd be fine too. It's just there's a lot of factors of 120. Okay. 1, 2, 3, 4, 5, 6. Let's go 8. I think 8. Lots and lots of factors of 120. Okay. So I might not want to use the rational zeros theorem here if I know this other piece of information. So plugging in all those different factors of 120 could get cumbersome. I know this other piece of information. So let's use that other piece of information. The other piece of information is I know another zero. Well, that's just like some of these previous problems that we've done, except for the zero that I know is a complex number, non-real complex number. Okay. Now, just off the top of our heads, does anybody know what another zero is? X plus 9. Exactly, the complex conjugate, right? We see that our polynomial function has integer coefficients. So complex zeros are going to occur in conjugate pairs. Just like irrational zeros occurred in irrational conjugate pairs. That's like we see. So we're forced to have three minus I as another zero. Now, there's actually a couple of different approaches to this. You could do synthetic division with a complex zero. That is possible to do, right? So you can do synthetic division with complex zeros. That's perfectly fine. But a lot of times people get mixed up when they're taking complex numbers times complex numbers, and it gets rough. Okay. Not impossible. It's very much doable, but not the greatest thing to do. So instead, what I like to do is a second option of seeing that x minus this number, by the way, I'm distributing the negative sign. So minus 3 plus I is minus 3 minus I. That's going to be a factor. And also, x minus this number is going to be a factor. I'll distribute that negative sign as well. So that means the product of these two things is going to be a factor of this. Since one is a factor, since this is a factor, since this is a factor, the product is also going to be a factor. And let's multiply this out. X times x gives me x squared. I'll multiply it out all the way through this time. Not every time will I do this, but x times negative 3 is negative 3x. x times I, that's a plus I, that's plus ix. So that's x times all three of those. Negative 3 times all three of these. Negative 3 times x, minus 3x. Negative 3 times negative 3, that's a plus 9. Negative 3 times I, minus 3i. Then I'll take negative I times x. Negative I times negative 3 gives me a plus 3i. Negative I plus I, that's going to be minus I squared. I squared is negative 1, that's plus 1. We're okay with that. Negative I times I is a plus 1. And then we do that thing where we notice that plus ix minus ix are going to cancel. Minus 3i plus 3i are going to cancel. I'll be left with x squared minus 6x plus 10. By the way, this is why they have to occur in conjugate pairs, because when they multiply like this, we get a quadratic with integer coefficients or real number coefficients, depending on, right? So, shortest version of this is that this is a factor of this. Now, I can't use synthetic division with a quadratic, but I can do long division with a quadratic. Okay, so I can't do long division with a quadratic, and that's what I'll do. X squared is what I need to get an x to the fourth. When I multiply x squared by that polynomial, I get x to the fourth minus 6x to the third plus 10x squared. Subtract the whole thing off. That would give me a 4x to the third minus 12x squared minus 32x plus 120. What do I need to multiply x squared to get 4x to the third? That's just 4x. X to the third minus 24x squared plus 40x. Subtract. Those cancel. Negative 12 plus 24 gives me a positive 12x squared. Negative 32 minus 40 gives me a minus 72x. 120 plus 0 gives me 120. Then what do I need to multiply by x squared to get 12x squared? The answer is, well, 12 times x squared is 12x squared. 12 times negative 6 is negative 72. So we get negative 72x when I take 12 times minus 6x. 12 times 10 is a positive 120. And sure enough, when I subtract, I get remainder 0. just like we knew we would. All right? So what does this mean? This is a lot of division work. We had to do some multiplication. We know this is a factor, and that is the same thing as this. Okay? So what this means is that when we divide f of x by this, we get x squared plus 4x plus 12. So we could rewrite f of x in one of two ways. Whoops. We can either rewrite f of x as x squared minus 6x plus 10 multiplied by x squared plus 4x plus 12. So that's one way. Right now I could rewrite it. Or the other way I could have rewritten that, since this was just a product of x minus 3 minus I times x minus 3 plus I could write it this way. Okay. Either way is fine. I know the zeros here. To find the zeros that this one would produce, I just set that quadratic equal to 0, and then do quadratic formula. Okay. I know I'm writing pretty quickly, but opposite of b would be -4, plus or minus the square root of b squared minus 4ac. That'd be 4 squared, 16, minus 4 times 1 times 12. And when I did that, I got a -32 underneath the square root. So I get a couple more complex answers. I had 2 complex answers, now I have 2 more complex answers. If you want to, 32 is 16 times 2. Square root of 16 is 4. So we could rewrite this as -4 plus or minus 4i times root 2, all divided by 2. Is that okay? So it looks like I have 4 complex zeros. I have the 3 plus I that I was given, the 3 minus I that I got by complex conjugates. And then I have this, which would be -2 plus 2 times the square root of 2i, or 2i times the square root of 2. Really doesn't matter. I can write that. Which order? And then -2 minus, I'll write this one in a slightly different order. 2 times root 2 times I. Is that okay? You care if the I or the square root of 2 comes first? It's both, it's the same either way. Is that right? So we were given a complex number as a 0, and we knew the complex conjugate was also a 0, so I knew this quadratic is a factor. So that means I can divide my polynomial by this quadratic evenly with no remainder. And then I know that my polynomial is going to be quadratic times quadratic, and I can find the zeros for both quadratics if I want. That one is probably harder than any one in the homework, to be honest. So that one's a really tough one. All four roots being complex numbers, unless I screwed something up. If I did screw something up, obviously. But I don't think I did. If I did, I probably would not have divided it down to 0 remaining. That's okay. All right. Now, in the same vein as that one, if I was not given any, well, let me reset to example 10. In example 10, all of my zeros were complex. Okay? What does that mean about the x-intercepts for example 10? None of them, right? There's no x-intercepts for that function. Okay? If I'm given another 4th degree polynomial function, and I'm not given any complex solutions, no complex zeros, then basically I would have to use the Rational Zeros Theorem and check and hope I get some real zeros, or hope I get some rational zeros. Because trying different complex pairs out would be really difficult to find. So if we're given a 4th degree polynomial function, we hope, we gotta hope like heck that one of those rational number options hits. And probably 2 of those rational number options hit. Since it's 4th degree, our rationals will occur in pairs too. That makes sense? So we try the Rational Zeros Theorem on 10, see if we get anything work, and hopefully things work. And if nothing worked, we'd kind of be at an impasse. We'd say, that's not very good. So that's what it comes out to be. That's all I'll say. And I won't do example 11. Again, you can try if you'd like to do that on your own, or watch video on your own. So that finishes section 3.6. What we're going to do in this class, next week, I will do 3.7, but we're going to skip 3.9, okay? We'll make that optional, and after we are done with 3.7, which is rational functions, we'll go straight to chapter 4, which is exponential and logarithmic functions. All right? So we'll skip 3.9. That being said, these 2 homeworks, 3.3.3.4 and 3.5.3.6, are both due tomorrow at 5. Okay? So make sure you get those 2 homeworks done. And then other than that, I will see you next time. Okay? All right.